All right, welcome back. So, before we start today's lecture, there are several notices or things that I want to mention here. So, first of all, the My Experience service has been open for a few days, and the school encourage all of you to fill out the survey as soon as possible. Right, the deadline of the survey is 13th of August. Right. So personally, I also want you to fill out the survey and give me as detailed feedbacks as you could. Right. So it is important for the course and also for myself, right, to improve. That is My Experience service. So by the time that you have seen this video, assignment 1 is already due. So assignment 1 has a firm deadline, so there's no extension. All right, no extension. And project 2 will be due. It's due this weekend. And make sure you have started. If you have not started yet, you should start it now and make sure you don't miss the deadline. Right. So for some students, if you want to ask for a special consideration, no matter it is for the project or for the final exam, you need to do it I think 1 week before the deadline, if I remember correctly. Anyway, you can search for the uni policies. But the thing is that I'm not the one who can give you the special consideration or extension. So I have to follow the university's policy strictly. So if you ask me, I will need you to apply for a special consideration from the university as well. So if you really need one, do it early. Don't do it like after the deadline or just 1 day before the deadline. It might be too late. The mark for project 1 has been released for almost a week. If you have not noticed yet, it's time to check your score. And I have for the final exam, right? For the final exam, it is a 1-day exam, so lasts for 24 hours. And however, the content or the workload of the final exam is not designed for 24 hours. So I guarantee you, right? Ideally, you would need 2 to 3 hours. It is just the workload is just like a normal final exam that you have been gone through in the past years. And the starting time of the final exam, I have put a pool in Piazza according to current statistics. We have nearly 200 students who have voted in the pool, and it seems that the winner would be either 10 a.m. or 12 p.m. So we would start from either one of this time, based on the result of the pool. I have put a post. I have posted a thread trying to collect the questions you have regarding the lecture contents. My original plan was to answer these questions. Well, my original plan is that through this post, I would be able to know like which part you're not clear enough, or I may not introduced clear enough, so I can fix that before we officially end all the lectures. But seems that you don't have many questions. so far I have only seen one, right? So I do encourage you to do it, and you also need to give me some time to prepare the revision slides. So it would be great if you can ask your questions as soon as possible. So projects, assignment, exams. Yeah, the for more detail about the final exam, we will offer more details about final exam in week 11. We probably will have a rehearsal final exam. The final exam is based on the Web CMS 3 system. Although we have not used that for our course in most times, but you must be familiar with it, because I see many CSE courses use this system. All right, so that's all for the notices, and now let's go back to the lecture contents, where we have discussed this. We just started last week. So the problem is to count distinct elements. So if the data stream has a universe of elements chosen from a set of size n, we want to maintain a count of the number of distinct elements seen so far. So that is the problem, and its applications we have introduced. The constraint is that we have a small storage. We have a small storage, and yeah, simply doesn't work. And we are going to use sketches. So here is the algorithm. So flagellate Martin sketch. It is a probabilistic counting algorithm for database applications. It is invented in 1985. It's an old algorithm. So the idea of this FM sketch is quite simple. Right? We pick a hash function h that maps each of the n elements to at least log n bits. So here the underlying assumption is that this hash function, just as all the hash functions that we have been discussed in L8, the hash function should be a perfect hash function. So the hash value of the elements is uniformly distributed. So what after we have this hash function which can map each element to at least log n bits. Now for each stream element A, we define RA. So RA is the number of trailing zeros in HA. So equivalently, I is the position of the first one counting from the right. So for example, if HA equals to 12, where the binary form of 12 is 1100, right? So the number of trailing zeros in HA is 2, right? Because we have 2 zeros here. Now if we counting from the right, so this position is 0, this is 1 because we count from 0, and this one, the position is 2. So RA is the position of the first one counting from the right. Now we record this R, the big R, which equals to the maximum RA that we have seen. So mathematically, it is the maximum over A. The maximum value of RA over A. Right. So it over all the items A seen so far. And then we magically have, not so magically, we will discuss why. So we will have the estimated number of distinct elements. So the number is 2 to the power of r. So let's look at an example here. So we have HA equals to, for example, 12, 11, 13, and let me see, 20, and 17. Yeah. All right. So this is this A, we don't know what they are. Just like A4. Maybe we have A5, which is 12 again. All right. So we want to know, we firstly compute RA, where if A1 is 12, so the RA is 2. For 13, the binary form is 1101, so it is RA is 0. For 20, it's 01000, so it's 2 again. 13 is 1301, so it's 0, and this is 2 again. Right. Then for the R, which is maximum of small r, RA, so it is 2. Now the number of distinct elements is 2 to the power of r, which is 2 to the power of 2, which is 4. Now this algorithm looks not that intuitive. I mean, why? I mean, it looks like, as I described it before, magically you would have this 2 to the power of r, which is the number of distinct elements, right? So, but it actually, the theoretical things behind this algorithm is not difficult as well. Right? So let's look at why it works. So this slide is an intuition of how it works, or why it works. So it is a very, very rough and heuristic intuition. Let's say HA hashes A with equal probability to any of the n values, as we have mentioned before. So underlying assumption is that HA is a perfect hashing function. So when HA is a sequence of log n bits, so hash value is a sequence of log n bits. Now where the 2 to the power of minus r fraction of all a's have tail of r zeros. Let's say we if we list all the binary numbers with log n bits, right, from let's say n equals to log n equals to 4, for example. So we start from 4 zeros, and you can keep doing this. So basically, we would have all the possible hash values with 4 bits. Right. Now, let's see how many of them have the tail of 1 zeros. How many of them has the tail of 1 zeros? Because if the tail has 1 zero, means it can be divided by 2. Right, for example, 0 and 2 So this is 0, 1, 2, 3, right? So on and so forth. This is 8, 9, so on and so forth. So if it can be divided by 2, it will have a tail of 1, 0. If it is cannot, then it would have a tail of 0 zeros. So how many of them can be divided by 2? Half of them. Right? So if we let r equals to 1, so it is about 1/2, which is half. So half of OAs has a tail of 1 zeros. Now, how about r equals to 2? Right. So if a number has a tail of 2 zeros, means it can be divided by 4. Right. So it is 1/4, which is also the 2 to the power of minus 2. So 25% of A hash value that has a tail of 2 zeros. It depends on whether it can be divided by 4 or not. Therefore, right, if we saw the longest tail of r equals to 2, means the item hash endings like 2 zeros and 1 here, then we have probably seen about 4 distinct items so far. Because we have about 1/4 chances that of the value is hashed to something with 2 zeros at the end. So it takes to hash about 2 to the power of r items before we see one with 0 suffix of length r. It means if say the r equals to maximum of RA, right? So if we have this r, then it takes to hash about 2 to the power of r items. So this is just a very rough and heuristic intuition. Now let's look at a more formally explanation of this algorithm. So we will show that the probability of finding a tail of r zeros, this probability goes to 1 if m is much larger than 2 to the power of r, and it will go to 0 if m is much smaller than 2 to the power of r. Given that you have find a tail of r zeros. And this m is the number of distinct elements seen so far in the stream. Also the number that we want to estimate. Now in this case, I mean let me see how to, let's say the RA, for example, they can be 1 or 2, 3, maybe we don't have a 4, doesn't matter, 5, 6, 7, and that's all. Right. So why we say 2 to the power of r will almost always be around m? Because now we have r equals to 7, means we have find a tail of 7 zeros. Right. Now for any now if m is much smaller than 2 to the power of r, which is 2 to the power of 7, right? Then the probability of finding a tail of 7 zeros goes to 0, which means m should not be much smaller than 2 to the power of r. Right. Now if we consider the value of 8, which we have never seen RA equals to 8, because the maximum of RA is 7. Now if say we have an m which is much larger than 2 to the power of 8, then the probability of finding a tail with 8 zeros goes to 1. In this case, we don't have a m that is much larger than 8. Then because we don't have a m that is much smaller than 7 either, which means we have this m almost always be around 2 to the power of r. Right? R is the maximum value of Ra, and if you describe it reversely, we could also say 2 to the power of r will almost always be around m. Now let's see how do we get this these two conclusions, right? So the probability that a given HA ends in at least R zeros is 2 to the power of minus R. We have explained this in these slides, right? So basically, HA hashes elements uniformly at random. It is a perfect hash function. And the probability that a random number ends in at least R zeros is 2 to the power of minus R. Or say it's 2 to the power of R, 1 over 2 to the power of R. So the probability of not seeing a tail of length R among M elements would be this. So we know that this part is the probability that a given HA ends in at least R zeros. So using a 1 minus 2 to the power of minus R is the probability that the given HA ends in fewer than R zeros. Because we're considering the probability of not seeing a tail of length R, right? So we have M elements, right? So the probability of not seeing a tail of length R, we times this for M times, right? So it is the probability of all ends in fewer than R zeros is 1 minus 2 to the power of minus R to the power of M. Now, if we change the form of this, it is essentially equal to because we times 2 to the power of R here and times 1 over 2 to the power of R here, right? It is a common trick that has been used at least in this lecture, L8, right? So this is approximately equals to e to the power of so it is just this part with a negative sign here, right? So this one is essentially this m times 2 to the power of r minus r is essentially m over 2 to the power of r. Right, so this part is equal to this. Now we have this is the approximate value of not finding a tail of length r. This is an approximate value of this probability. So if m is much smaller than 2 to the power of r, then the probability tends to 1, right? Because when m is much smaller than 2 to the power of r, m over 2 to the power of r approaches 0. So e to the power of 0 is 1. So this whole part equals to 1. Right? So the probability tends to 1. Now, if m is much larger than 2 to the power of r, the probability tends to 0, right? Because when m is much larger than 2 to the power of r, m over 2 to the power of r tends to infinity, right? And this part, e to the power of infinity, tends to infinity as well. So 1 over infinity is 0. So the probability tends to 0. So the probability of finding a tail of length r tends to 1. Yeah, because the probability of not finding a tail of length r tends to 1 or 0 here. So the probability of finding a tail of length r tends to 0 or 1. Right, so it is just using 1 minus this probability. Therefore, we have the conclusion that 2 to the power of r will almost always be around m. So far is the theoretical part of how do we do this FM sketch. So empirically, now what we do in order to implement a FM sketch, what we do is that we maintain a bitmap array of L, which equals to log n bits, and we initialize the bitmap with all zeros. Now for each incoming value A, we compute HA, right? And then we can have RA, and we set FM at the position of RA to be 1. Now, as you can see the example here, so essentially it means that we have seen at least one element whose RA equals to, I don't know if this is 1, 2, 3, 4, 12, right? And we haven't seen any elements with RA equals to 11, because that's why here is a 0, right? And so on and so forth, and so on and so forth. Now, if we have D distinct values, then we expect that D over 2 maps to FM of 1, right? And D over 4 maps to FM of 2. The reason we have already discussed before. Then you can imagine the expected number of elements that maps to FMX. With a larger x, the expectation of the number would be smaller, right? Would be smaller with a fixed D. So we use the leftmost one, which is 12 here, and then we can get this big R. Right. So the estimation would be 2 to the power of R. In the original paper, it also uses the rightmost 0. So in this example is the 0 here. So it uses it as also as an indicator of log D. Right. So if we use the rightmost 0, then we estimate this D equals to C times 2 to the power of R. So in this case, this R is 9. And for scaling, with the scaling constant, that is C approximately equals to 1.3. We don't have time to illustrate this in this course. So if you are interested, you can refer to the original paper. All right. And apparently, if we have multiple hash functions, or different hash functions, then we can average many copies to improve the accuracy. And this is a commonly used technique to improve the accuracy. All right, so that's all for data stream. Now let's move to next topic. Also is the last topic in this course, which is recommendation system. So recommender system or recommendation system is a kind of new topic in big data or data analysis. It is closely related to the development of the e-commerce. So today, I mean, many people shopping online, right? Buy things from Amazon, for example, or eBay. So the customer or the user actually search for items. If we use the e-commerce example, so they search for items to buy, and although these items could be products or websites, blogs, and news items, depends on different platforms. then the system will not only returns the item to the user, but also the recommendations of other items to the user. Right? I believe you would have such kind of experience when you buy things in Amazon, or when you watch a movie in Netflix. It will give you some recommendations of other movies, saying, "Oh, you might be interested in watching this," or other people also watches this movie. Right? For example, this should be Amazon, right? When you search for this book, it actually recommends you, saying that customers who bought this also bought these books. Right? So this is the example of the usage of recommender systems. Right? It also can be used in movie recommendation, for example, in Netflix, related product recommendation in Amazon, where you have been seeing already, web page ranking in Google. It is not that obvious, but actually Google using similar idea, or has converted the problem into a recommend system problem in order to rank the web pages for you. Right? And social recommendation in Facebook, right? It recommends you with new friends or new post, for example, right? Right, these are an example of Netflix movie recommendation. The data set actually comes from a competition that is hosted by Netflix. So the goal of the competition is, say, giving you this training data. It asks you to predict the score in this test data. So all you have is the user ID, the movie ID, date, and the score. So the score is the is the star that the specific user gives to the specific movie on the specific day. Right? So for test data, it actually masks the score. So the competition is asked you to recover or estimate the scores here. So this is a very famous competition, and the main idea of how to solve this problem is to use the algorithms or methods in recommendation systems. Right? And if we have enough time, in Wednesday, if we still have enough time, we may be able to see some best solutions, right, for this competition. Now, why using recommender systems? So the value for the customer is that it helps the customer to find things that are interesting, and also narrow down the set of choices, help you to explore the space of options, discover new things, and also for entertainment. Well, all these things are straight enough, so I won't explain them in detail. And the value for provider, where for the provider, it would have additional and probably a unique personalized service for the customer, and it will increase the trust and customer loyalty, because the customer would have a better experience. It increases sales, click-through rates, or conversion, actually, and also the opportunities for promotion and persuasion. And it helps the provider to obtain more knowledge about customers. This part is not that straightforward, but through what we will discuss later, hopefully you would have the idea of why this can be counted as the value of recommender system for the providers. So if we abstract the problem of recommender systems, so we actually seen it as a function, So if we have, if it is a function, then it has input and output, right? So the input is a user model, like the ratings or the user's preferences or demographics, situational context, and also the items. For the items, we may have or have not description of item characteristics. So more user and items are the input of this function, and the output of the function is the relevance score. We use this relevance score for ranking, and we only show the customer or the user those items with a higher ranking. So finally, we recommend items that are assumed to be relevant or have a higher ranking. So the idea of the whole recommender system, how it works, is like for a particular user, right? We build a user model or not, depends on the algorithm, and for a given user, we actually try on different items and do the prediction, right? We kind of estimate the relevance score, and then we can rank the items based on the score and recommend items to the user, right? From those with higher scores. Although there are some issues or problems, say that, for example, the relevance might be context dependent, so it actually raises a higher standard, all right, or more requirement or more strict requirements for the recommender systems, right, when it estimates the relevance score, and also the characteristics of the items or of the list itself might be important. So here the list actually refers to the recommend items. So we may also have the requirements or have the constraint on the recommend item lists, items list. Right? For example, we want it to be diverse. For example, you are searching for a dress. Right? So one way one way for the recommender system to give you the recommended items list is to give you a list of other dresses. But a better way might be to recommend you with, for example, the hats, the shoes, right? Such kind of things that they are relevant to the dress, to the dress, but they also have the diversity in the list. Right? I'm not an expert of fashion, but it seems that the latter way is better. Now, if we describe it using a formal model, say X is a set of customers and S is a set of items, then we want to have a utility function U. So U takes X and S as the input, or more specifically, a matrix of X and S on the different dimensions. So the function maps this matrix to R, where R is a set of ratings, and R is a totally ordered set. The values in R can be either 0 to 5 stars, or a number, a real number in between 0 and 1, right? So here is an example, right? This Alice, Bob, Carol, David, apparently they are X, the set of customers, and then these are the S. So these are the items, right? Actually, they are movies. They are movies. So what you will do is to predict the empty cells here, using real numbers between 0 and 1. Now the key problems of in order to solve such a problem, such a problem. So the key problems here are first of all, how do we gather known ratings of metrics? So these numbers are the already known ratings for the metrics. So in order to solve this problem, there are several key sub-problems that we need to pay attention with. So first of all, how do we gather known ratings for metrics? For example, here the circled ones are the already known ratings. We need this to help us to build the function, also to do the prediction. So essentially, it is about how to collect the data in the utility matrix. Also, we want to know how to estimate those unknown ratings from the known ones. And also, we're mainly interested in high unknown ratings, because the system are always supposed to recommend what it thought the users would be interested in. Right? So which are those with high ratings. So we're not interested in knowing what you don't like, but what you like. Also, how do we evaluate these methods? Right? How to measure the success or the performance of the recommendation methods. So these problems, we're going to address them one by one. Right? So we start from gathering ratings. So this part is relatively easy to do. Right? There are several ways to gathering the ratings. There are explicit ways, like we just ask people to rate items, right? It does not work well in practice because many people don't like to be bothered. Actually, myself is one of them. I usually don't rate any items. But you must have this experience. For example, if you use iPhone, then many applications will ask you to rate it in the application store. Implicitly, we can learn the ratings from user actions. For example, if the user purchases an item, then it must mean that she implicitly gives a high rate of that item. Or for example, if we see a movie and we close it in 5 minutes, means we don't think it's a good movie. Right? Although we don't rate the movie, but you can imagine if we rate it, we won't give it a high score. So here are the two ways of gathering the ratings. Now the second problem is how do we estimate the unknown scores. So here are some paradigms of recommender systems. So in general, recommender systems reduce information overload by estimating relevance. So the problem here is what kind of relevance does it estimate, right? So one way to do it called personalized recommendations, where we will need a user profile and contextual parameters. So we use this to give the as the input to the recommendation components or recommendation systems. Right? We will generate the recommendation list. Also, the collaborative one. So the essential idea is to tell me what's popular among my peers. So the idea is like, okay, A and B are friends, right? A and B are friends. They have similar taste, So when A buys something, then the system would think that B should also be interested in that. So this is the collaborative idea of recommendation systems. We will discuss this later. And also the content-based one is the idea is to show me more on the same what I've liked. So by this one we actually estimate the relevance between users. But for content-based one, show me more on the same show me more of the same what I've liked. So it actually estimates the relevance between items. Like if I bought I've bought item A, and if we know that if the system knows that A is similar to B, then it will recommend B to me as well. Right. Or knowledge based, tell me what fits based on my needs. So this usually used together with the item informations, or say product features. Or the hybrid one, so it's a combination of various input or the composition of different mechanism. So in this course, we will give a brief introduction of several paradigms of recommender systems. So we start from a content-based recommendation. So the idea is to show me more of the same what I've liked. The main idea of content-based recommendation is to recommend items to customer X that is similar to previous items rated highly by X. In order to do that, we need to know some information about the available items, such as the journal or the content, and also some sort of user profile describing what the user likes or the user's preferences. For example, for the in the movie recommendation systems, we recommend movies with the same actor or director or genre, right? And for websites or blogs or news, we recommend other sites with similar content. So this is an example of content-based recommendation systems. The user, we know that it likes these items. Then we trying to extract the item profiles through these items. Right? So what we have extracted is that so these items are red, right? And circles or triangles. Then along we use this as well as the user profile. From this we've got the user profile, or say what the user likes, and then we do the match with the items we have or in the database. Then we would have this one as it is red, this one as it is a circle, but for these two, they're not so relevant with the user's profile or what the user likes. So finally, we will recommend these two to the user. So now let's stop here and have a break, and we will come back and introduce what is the how do we how do we solve the content-based recommendation problem?